try to study ahead of time, I think that's great. You know, that's the purpose. I post everything online, so you can preview the material. All right. Okay, let's go through some logical quantifiers. So previously we already used and, or, not, and to left hand side implies to right hand side, and if and only if, or necessary and sufficient condition. So we use those to combine statements. Right. Let's see some symbols. So this symbol is like upside down A, means for all. Okay, for all. So later on in mathematical proofs, we use these kind of symbols all the time. You know, for all x in a set of real numbers, right? We would use this symbol for all, or for every x in real numbers. And then this one it's like a flipped to the right, E, right? This means there exists, or there is something. So this is a there is symbol. Sometimes if we want to represent there is a unique value, we would put an exclamation mark after there is. So for all and there is are called quantifiers. So if a statement contains those quantifiers, then the statement is called a quantified statement. Let's see some examples. So in English, we can say for all integers n, 2n is even, right? For all integers n, 2n is even. So n represents any integer. And in the quantifier, we can represent it like this. For all n in the set of z, z represents integers, 2n is even, right? So for all n in the set of z, 2n is even. See the second example, there exists a subset x of n. Remember this n means natural number or counting number, 1, 2, 3, so on and so forth, for which absolute value of x equals to 5. So this becomes there is an x, right? And such x is in the, okay, this is a subset. This x is a capital letter, so it's a subset. So there is a subset x of natural numbers. And so we want to see and, right, for which, and this condition exists. So we would do and absolute value of this set equals to 5. So the symbol for all is called a universal quantifier. And the statement containing this quantifier for all is a universal quantified statement. The symbol that exists is called existential quantifier. And the statement containing this is called existentially quantified statement. Those, you know, those terms are not so important, but the ideas, just get the ideas. You know, how we use for all and they exist. Let's see this one. Every integer that's not odd is even. Every integer that's not odd is even. So we can translate it into for all n in the set of integer. You see this n is like a variable, right? You can see for all x, doesn't matter. For all n in the set of integers, negate not. So n is odd inside the parentheses, right? So we want to negate this set. So n is odd, right? That's a set. So not, or we can treat it as a statement. And this is an open sentence, right? Open sentence. So not, so I negate this expression, n is odd. So that means, you know, not odd. That means even, right? Not odd, then means implies n is even. So we can translate it into this kind of, you know, logic and statements with this implying sign. The next one, for every real number x, there is a real number y such that or for which y cubed equals to x, right? So for every real number x, right, it's a cube. So cubic, it's someone's cube, right? There is a real number y for which y cubed equals to x. So which, or we can think of this as for every real number x is someone's cubic, right? We can read as for all x in real number, there exists y in the real number also, and such equation holds y cubed equals to x. So we see the advantage, right? Using these quantifiers, you know, we simplify the English, the sentence. The statement for all x in the set S, P of x. So let's see this expression. For all x in the set of x, P of x. For some set x and some statement P of x, so remember P represents a statement. Right? And this statement includes x, which makes an open sentence, right? Every statement has a variable. We cannot tell if it's true or false. We call it open sentence, which depends on x. It's true if it is true for every x in the set of S. Likewise, the statement that there exists x in the set of x, P of x is true if there is at least one element x in the set of x for which the statement is true. Okay, we use this all the time in mathematical proofs. Let's see this. There is an integer n for which n squared equals to 2, which is a false statement, right? So if we translate in, if we use the quantifiers, we see there exists an n in the integer set, n squared equals to 2. We can write like this for every real number x. So now it's real number x, right? Remember here, for every real number x, there is a real number y for which y squared equals to x. Use quantifiers, we write for all x in R, or for every x in the set of real numbers. There exists a number y also in the set of real numbers, and y squared equals to x. Anyone has any questions so far? Okay, let me know when you have questions. When there are two same quantifiers in the statement, the order does not matter. Let's see this one. For all x in the real number and all y in the real number, x plus y equals to 4. right? Or we could change this one to say for all y in real numbers, for all x in real numbers, and the y plus x is 4. Okay, so order does not matter. They are the same statements for all x, y. So we don't have to separate x and y in this case because x is an element in the real number, y is an element in the real number. So we can write all at once. We can write as for all x, y in real number set. Right? X plus y equals to 4. This is saying, okay, the comment here, note this statement is false, right? If, however, you replace all the for all with there is, it'll be a true statement. So when there are two different quantifiers, the order of all for all and there exists matters. Let's consider the following two statements. So for all x in R, or for every x in the real set, there exists y in the real number set, y cubed equals to x. If we switch those two quantifiers, we see for all there exists y in the real number. For all x in real number, y cubed equals to x. Right? Right? That would be different. That would give us a different meaning. So we have to be careful the order when we mix for all and there exist two quantifiers. Okay, so this talking about the two quantifiers for all or for every, and this one there exists or there is a. So second thing for today, we'll talk about more about the conditional statements. Right, we already talked about this. If left-hand side, then right-hand side. X is a multiple of 6 implies X is even. If we turn around the statement, if we say if X is even, then X is a multiple of 6, it can be true for some X, but it will be false for some other X. So it does not, so we cannot flip. We cannot flip the left-hand side and the right-hand side. And we talked about last class, we talked about a control positive, right? So control positive is we left-hand side implies right-hand side is the same as we negate the right-hand side implies the negation of the right-hand side, the left-hand side. That's called a control positive. So the control positive is true. Right? X is even. If X is even, then X is a multiple of 6. Doesn't work. We can use a quantifier to make it into a statement. So let's say this one. For all X in the set of integers, and X is even, right? Sometimes we would write for all X in the set of 2Z. Instead of writing X is even, we can write X belongs to the set of 2Z, right? So 2Z represents all the even integers. So X, the even integer, implies X is a multiple of 6. Right? We can write this way. In general, for two open sentences, depending on the variable x. So one statement contains the variable x, and another statement contains the variable x. Let's see this one. So this one is saying for x, for all variable in a set S, one statement, one open sentence, right? One open sentence with variable x implies another open sentence contains x. Conventionally, if a conditional statement does not have a universal quantifier in front of it, then there is implied universal quantifier in front of it. So sometimes it's by default, right? It's like when we talk about a variable x in mathematics, right? There's one x and x raised by first power. So some just convention, by people agree upon. The conditional statement is true if it is true for all the variables in it. It is false if there is at least one variable or which it is false. So let's see the true statement. If x is a multiple of 6, then x is even, right? So this is true. This is true. So P implies Q. But if we do the reverse, it would be false. If x is even, then x is a multiple of 6. That would be a false statement. But however, just to remind us of the control positive we talked about last Thursday, if we negate this one, we say if x is not even, then x is not a multiple of 6. That would be true, right? That's called control positive. Okay, let's make some definition. If P and Q are two statements or open sentences, then if P then Q is a statement. Right? So we're combining two statements. We're combining two statements which make one statement. As you can see, of course, we can combine finite many statements, right, to make one statement. Okay, so this is a little more about conditional or statements use the two quantifiers. Okay, let's see, we translate some English into symbolic logic. Let's see an example of intermediate value theorem. Right? The intermediate value theorem is saying if f is continuous function on an interval, closed interval from a to b, and n is any number between f of a and f of b. Right? So n is in the range, right? But it's in between f of a and f of b. Think about the x-axis and the y-axis, right? So this n, so f of a, f of b will be on y-axis, and n is a number, right? N is a number on y-axis, but between f of a and f of b. And on the x-axis, think about a and b, right? Think about one number a here, another number b here, where f of a not equal to f of b, right? If f of a equals to f of b, then n has to be f of a, f of b. Then there is a number c in AB such that f of c equals to n. But just imagine what you can draw. You can draw x-axis, y-axis, so xy plane. On x-axis, you have AB interval. Then on y-axis, you have f of a, f of b interval. Suppose those two not equal to each other, so you have an interval. Then n is a number in between of f of a and f of b. So the intermediate value theorem says then there must be a c in between of a and b, such that f of c equals to n. Okay, that's intermediate value theorem in Math 150. Now, let's use quantifiers for this theorem. So f is continuous on closed interval a, b, and n is a number between f of a and f of b, where f of a not equal to f of b implies there exists a c in the interval a to b, such that f of c equals to n. Okay, so we using this, there exists a quantifier. Let's see second example, composite limit theorem. If f is continuous at b and the limit x approaches to a, g of x equals to b, so that means the function g has a limit when x approaches to a. Right? Remember, the limit means x approaches a from the left equals to x approaches a from the right. And also in this case, right, equals to b. And the limit is b. Then limit x approaches to a, f of g of x of equals to f of b. Okay. So composition functions. When we talk about the composition of functions, and we can talk about the composite limit. So this is composite limit theorem. So let's see, we want to use some quantifiers in this. So we say f is continuous at b, and at this end we switch to this end sign. Right? Consider f is continuous at b as a open sentence. Limit g of x equals to b as x approaches a as another statement or open sentence. And we use this and sign. And this becomes one statement. So and sign combines those two statements into one. And this implies to another statement. Limit of f of g of x equals to f of b when x approaches to a. All right, so this, we use those quantifiers in mathematics theorems. So for negating statements, so if we have statement P, we want to negate P, we use this symbol, not P. So with De Morgan's laws, we have this kind of relationship. Not P and Q means not P or not Q. Not P or Q equals to not P and not Q. Right? So this is called De Morgan's laws. Assume P of x is some statement dependent on x, which is an open sentence. Then we want to negate the statement. For all x in the natural number set, then statement P of x. For all natural numbers x, or for every natural number x, the statement P of x is true. To negate this statement, we would have, it is not the case that we want to negate the whole thing. So it's not the case that the P of x is true for all natural numbers x. This means that there is at least one natural number x for which the statement is false. So in symbolic logic, we use this. So not, we negate the statement. The statement is for all x in natural numbers, P of x. Then we want to negate the whole thing. Negate the whole thing, because this is for all. When we negate for all, that means there exists at least one. Right? There exists one natural number, and this, which negates, and that number will negate the statement P of x. You know, we always use, a lot of times we use this kind of strategy. to prove, to do mathematical proofs. You know, we want to find one counterexample. You know, as long as we can find such x as a counterexample, you know, we disprove something. Okay, in general, negating a statement with for all involves there is, and vice versa. If you want to prove there is something, right? If we want to negate, we would prove for all. Let's see the symbols. So we want to negate this statement. This statement for all x in the set of x, p of x. We want to negate this. That means we can prove, that's the same thing to prove that there exists one x in the set of x, which negates p. Same thing, if we want to negate this statement, there is one x in the set of x, p of x. You know, we can prove that for all x in the set of x, you know, which negates p. Sometimes we need to negate a statement which has multiple quantifiers. So for every real number x, there is a real number y for which y cubed equals to x. In the symbols, it looks like this. For all x in the real number, for all x in the real number, or for every x in the real number, there is one y. Also in the real number, y cubed equals to x. Now let's negate this statement. Let's see, how do we negate this statement? So the statement is for all x in the real number, there is one y, at least one y, right? So there is a y in the real number, y cubed equals to x. We want to negate the whole thing. Remember, when we negate for all, we use there is. When we negate there is, we change to for all. And also, so let's see this. So negate for all, that becomes there is a x in the real numbers, and the negate there is becomes for all. Okay, so that becomes there is one x in real number for all y in real number, negate y cubed, so which is, this is not true, so y cubed not equals to x, right? Because when we negate this, you know, combined statement, we have negated everything. So we can write as this. We can write as there is one x in the real number, or there is one real number for all real number, and such thing is true, which means y cubed not equals to x. So that's a negation of the whole statement. The important negation for proofs later is following, which can be shown by a truth table. So P implies Q. We want to negate this. Not P implies Q. Right? Not of P implies Q. So that equals to P and not Q. We can use the truth table to prove this. Well, let's try. Let's prove this, and also to. Actually, this is obvious, right? This is obvious. So P implies Q, right? That means not not P implies Q. Not P implies Q. That's P and not Q, right? Okay. If you have doubts, you can use the truth table to prove this. All right, we know how to use the truth table to prove this. Okay, anybody has any questions? Great. I think probably all of you have read this. Let's try some classwork. Since tomorrow is midterm, so we're going to talk about tomorrow's exam later after we finish this. Okay, so 1 has 4 questions, right? So A has 1 and 2, and B has 1 and 2. So try those 2 questions. And maybe some of you have done already. And I would like someone to volunteer to talk about those, to give your answers, to explain your answers, to earn your participation grades. All right. Oh, that's fast. I'm checking the attendance. Okay. Whom are we missing? Oh, George was late. Okay. Now let me take a new picture. Okay, great. Great, yes. Yeah, we could see for all x in the real number or for every x in the real number. Looks good. Okay, nice. Okay, now what about for B? Good job. Okay, Jaya, I'm not seeing your answers. And George, I'm not seeing your answers. Let me see who Maria has. Also Michael. Oh, Michael has. Yeah, so far I haven't seen Jaya and George writing any response yet. Okay, B for all x in real number. Yes, pretty simple, right? All right, anyone has any questions? Okay, let's keep moving. So let's see, two are the following true statements. You know, which one is true, which one is false. So three, so two has A, B, C. True, false, truth. So Jinqi, you only read false. I'm not sure which one you're talking about. Yeah, like Michael's A, B, C, you know, A is true, B is false, C is true. Oh, how do we know if it's true? Aidan is asking, right, Ajaya, also you only read true. Which one is true? You mean 1, 2A? So let's see. So 2A, so we think it's true. 2B, we think is false. And 2C, we think is true. A is saying if x is a real number of R, then x squared plus 1 is greater than 0. This is true, right? Because think about the smallest x squared, smallest value of x squared, that's 0. Right? That's 0. So 0 plus 1, of course, is bigger than, so it's 1. 1 always bigger than 0. So that's first one. 2b, if p is a prime number, what are the primes? Prime numbers has two factors, 1 and itself. So then p is odd. Is this true? B is false, right? Can anybody tell why it's false? Because 2 is a prime number and it's even. Great. 2 is the only prime number and even. 2 is the smallest prime number and is the only even prime. So B is false because 2 is prime, but the 2 is even. C, if a function f is differentiable on R, then f is continuous on R. This is true, right? The inverse wouldn't be true, but this is true. If a function is differentiable, it's continuous. But if a function is continuous, it may not be differentiable, right? Let's see absolute value a function, right? Which is a continuous function, but it's not differentiable. Okay, great. Anybody has any questions about 2? All right, let's keep going. So 3. So we want to convert the following statements with the symbolic logic. So 2 questions, 3A, 3B. Great. Yeah. Great. Looks good. So I guess for you guys not writing A or B, I'm just assuming it's A. All right. Xiaoming, if you want to use P for all P, the first P read a lowercase p, just like your Q, right? Because you want to use a bigger P for set, you use the lowercase p for element. Looks good. Okay. Patrick, your second P has to be a capital letter P. You cannot use a 2P. So lowercase p belongs to is a element of lowercase p. Doesn't make sense, right? So first P, right, use lowercase. Second P, use a capital case. You could just read it as A, right? For now, right, in this chat, I don't think we're able to read upside down A, just read A. So we all know what it means. Yeah, P is in P. Oh, actually, you guys found the for all. For all, and oh, you just copy and paste? I see. Okay, great. For all P, right, in the capital P. Okay, good. So good, great. Yeah. All right, looks good. Anybody has any question? All right, great. Let's see, 4. We're going to negate those statements. Remember, we want to negate the statements, okay, the whole thing. You can solve it by factoring or. How do we negate or? Use the De Morgan's laws with the quadratic formula. Okay, guys. If you copy paste from your work, so make sure you identify your P and your Q. All right, you want to use shorthand. So I guess for Maya, P probably is you can solve it by factoring, right? And the Q is with the quadratic formula. So not P and not Q. Great. Yes, that's De Morgan's law. B, the number X and Y are both odd. So not X, not X, Y are both odd means not P or not Q. Yes, which means as long as one is not odd. So it's not X being odd or not. So X is not odd or Y is not odd. Right. If you want to use a sentence, you cannot solve it by factoring and not with quadratic formula. Yes. So De Morgan's law. right? You can use neither nor, okay. You can neither solve it by factoring nor with the quadratic formula. Okay, by doing this, you just changed. Okay, great, yes. You just negate the whole thing, yes. That's what we use in English, neither nor, great. Okay, George, are you here? I don't see you writing anything. Also, Ajaya doesn't read much as well. Oh, okay. Now I see Ajaya's. Oh, okay. That's great. Okay, we're here to learn. Ajaya is saying, I don't understand C. C is saying the square of every real number is non-negative. That's the definition of real number, right? So how do we define a real number? The definition of real number is a number multiplied by itself will never be negative, right? Think about -2. -2 times -2 will be +4, right? Think about 0. 0 times 0 will be 0, right? It's not negative. So that's the definition of real number. When you square a number, has to be at least 0, which means it's not negative. If we negate the whole thing, the square of every real number is non-negative. It's not true, right? Jin, she's saying not every square is negative. Not every square is negative. Okay, that makes sense. Square of a real number is negative. Yes. The square of every real number is negative. Remember, how do we negate all? When we negate all or every, when we negate, that becomes there is, right? Or there's some, that's okay. Some, or there is, or there are some, yes. So when we negate for all or for every, that means we use there is. There exists the square of a real number. That's negative, right? So, okay, so remember, so this is a combination of De Morgan's law, and when we negate for all, that equals to there is, that, there is some, or there is a. When we negate there is, that becomes for all, for every. Okay, anybody has any questions? What was C? The C, someone give a perfect, let me see, let me check who gave the perfect answer. Oh, here, you see Maya's C. Let me copy and paste. Which is not true statement anymore. Okay? Right now, C is a true statement. C is just a definition of real number, but when we negate, it becomes false. So the negation of the whole statement, we can write as there exists, some number or a number whose square is negative, or like Maya is saying, there exists the square of a real number that's negative. Well, I think better to say this way. There exists exists a real number is negative. There are a couple of ways of saying it. So I would say this. I would say there exists a real number whose square is negative. And of course, this statement is false. Because when we negate a true statement, the statement becomes false. Okay, any other questions? All right, let's keep going. Okay, let's try 1, 2, 3. So 1, convert, we want to convert those symbols, these quantifiers, into English. And also find out if it's true or false. For the first one. For all n in the integers, there is a subset of natural numbers, and the absolute value of the members in the subset X equals to n. All right, let's see. For every integer n, Samuel, is for all integers. Okay, for every integer n, oh, that's fine. For every integer n, there exists a subset X of n of a natural number where absolute value of X equals to n. Yes, okay, looks great. Moise says for every integer n, there is a natural number. There is a natural number set. Well, you have to see that's a number. That's a subset of X. There is a natural number set of X. You have to you have to see there is a subset of natural numbers, right? There's a subset wiggly parentheses with X of natural numbers such that absolute value of the members in the set equals to n. Okay, looks good for every Yeah, subset of natural numbers. Okay, looks good. So what about the statement? Is the statement true or false? Is the statement true or false? True? True? Remember n. N is an integer. Integer can be negative. How can the absolute value of something be negative? It's a false statement, right? Okay, let's see who wrote. Okay, Aidan was the first one to make true this statement, and all the rest of you just following him. It's a false statement, all right? Any questions? Why it's a false statement? Isn't that assuming the subset is all negative? No, the subset belongs to natural numbers. Aidan, what are natural numbers? Counting numbers, right? 1, 2, 3, 4, all positive. If we switch those two, right? If we switch those two, if we switch z and n, that will make this statement true. But currently, this statement is false. All right, so let's see second one. Convert to a statement with for all and there is. State if true or false. there exists a number y in real number for all x in the real number, xy equals to 1. Right, okay, looks great. Or we can use this imply sign. Great. Okay, looks good. Okay, is it true or false? I see someone saying true, someone is saying false. False, right? False. How can we make second one true? Like the first one we switch z and n, we would make the statement true. For the second one, if we want to make this statement true, what should we change? Oops. We don't want to use the for all anymore, right? We would say there exists a real number y and a real number, there exists a real number x such that xy equals to 1, right? We want to change the second condition for all, for every, to be there is a. All right, good job. Okay, 3. Is this a statement? It is true or false. If f is a rational function, then f has asymptote. What are rational functions? Rational function means x appears in the denominator. If x is a rational function, then f has an asymptote. Let me give you an example. F of x equals to 1 over x squared plus 1. I just made one rational function, 1 over, so 1 is the numerator, denominator is x squared plus 1. Three is a true statement. George is saying is a false statement. Statement like this and a function like this is obvious, right? We have a vertical asymptotes. But what about my first function? We don't have a vertical asymptote, but however, we have something else. We have horizontal asymptotes, right? So it's a true statement. We either have vertical asymptotes, or we have horizontal asymptotes, or we may have both. Okay, great. Anybody has any question? Okay, that's all new material for today. So let's talk about tomorrow's exam. So I think you're probably very prepared, very well prepared for tomorrow's midterm exam, right? Well, anybody has any question regarding tomorrow's exam? It will take the whole class time. Number of questions, let me see how many questions. I'm going to show you. I'm going to show. I'm going to show you where to find the exam, but let me check how many questions. Ten questions. 10 questions plus. Let's see. But of course, each question has like A, B, C, D, right? Have different parts in it. Okay, so 10 questions, but plus 1 extra credit. All right, so extra credit is just extra. Okay. Let me see your questions. How many questions? So 10 questions plus extra credit question. Yes, we're taking on Blackboard, just like this, right? So you need to turn on your camera. You need to have your student ID with you. So before taking exam, you need to show me your ID. So your ID needs to match up with you, you know, who's taking the exam. And let me see what else. Okay, stop typing more questions for now. Let me read these questions. When I finish answering those questions, you can type in more, all right? So 10 questions plus extra credit. We're taking on Blackboard, just like this, in class. So you need to turn on your camera, have your student ID with you to verify it is you taking the exam. Michael, I'm going to show you where to find the exam, all right? You have to submit your exam through this CUNY Blackboard. I will show you where to find it. Is the midterm based on the fact formula? Yes. It's based on, you know, the material we have learned. Yeah, I will. Yeah, I will let you know where to submit. It's similar to, you know, you submitting your homework. Patrick, if you don't have a Hunter ID, then prepare your. You have other ID, right? You have other picture ID. So just use other picture ID. Yeah, use your other picture ID. So, you know, as long as your name is on there and with a picture, that will be fine. Okay, Maria, use another picture ID, all right? George, same thing. If you don't have a Hunter ID, use another picture ID. Xiaomin, same. Oh, okay. So most of you don't have a Hunter ID. That's okay. You know, your high school ID, your driver license, you know, any picture ID. How much time? It's the whole class time, 2 hours. But if you finish, you submit, you finish early, you can leave early. Oh, okay. That's a good question. Okay, stop typing more questions for now. Let me answer this question. So Adan is asking, so with our camera on, do we have to look at the screen the whole time? What if I'm using sweat paper to write my solutions on or drawing a truth table? I see. So you want to use your computer, right, to write your. Yeah, you need to keep the camera on. The truth table, draw by hand. Draw by hand. Okay. So it's an open book. So which means you can consult with your homework, with your notes, but you won't be able to use your computer. Okay, so draw the truth table by hand. Yeah, camera on the whole time. Yes, Samuel. Yeah, your ample ID is your student ID. Does it start at 1? Yes, right. Our class start at 1. Yes, it start at 1. So we'll hopefully you can get on a little early. If not, because I have to check your identification, your ID, maybe we start like 1:10. If we did start a little late, I'll give you more time. So we will finish by 2:10, something like that. All right. So you will get 2 hours to finish the exam. Moises is asking where is going to take place. I'm going to show you, where will be the submission button. And the submission is exactly same as your homework submission. The process is the same. Yes, you can upload as a PDF file, or you can most students take a picture, Oh, okay. One more thing. Once you finish, right? Once you finish, you take a picture. You need to put your ID somewhere on the corner of your exam to verify, you wrote, you finished the exam. So your ID, doesn't matter what kind of picture ID. So you take a picture of your exam with your ID on each page. So write your name on it. So have your name on it, your ample ID, your student ID, your name on the exam. And when you take a picture, you take a picture with your picture ID with together. Let me see. Open book. Open book means you can set aside your notes. All right, your notes or your homework. No, Patrick, you have finished your homework, right? Right. Use your homework, not a textbook. Okay, Shamika is asking, how do we do it? What do you mean, how do you do it? You see, right now, you are on, right? You're using your computer, right? So the only thing we did not do at this moment is we did not turn on our camera. But tomorrow, all of us need to turn on our camera. Okay, I need to verify every student. So you need to have a picture ID. And also, when you submit, before you submit, you need to take, because you need to take a picture of your exam, right? So you take the picture of your exam with your ID, with your picture ID. No, digital notes are not open book. Samuel, because you need to have your camera on the whole time. You won't be able to use your computer. So everything you have in what? So in that case, you have tonight. Make some notes. Make some notes if you think you need to have some notes. What do you mean? So Moise is asking, The camera being on during the exam, is it in this room? Yes, it's right here. We're taking exam right here. No, you're not allowed to use your computers. You can only have some written down notes on your side. I'll let you know where to access the exam. Shamika, right, you need to put your picture ID on the side of your paper, exam paper. Yes, you need to take pictures together. The exam is digital. It will be on your screen, right? Yes. Yes, Patrick. You need the computer, right, for your PDF exam. Okay, Maria, why not? Your camera on is your camera on, right? So you turn your camera on. Then you click on the button. Let me show you where to find the, take a picture with a phone, then email that to you. Right, either you scan or you take a picture, right? Most students take a picture, right? You take a picture of your exam paper with your ID, or if you have a scanner, you scan your exam with your picture ID, then you submit. Yeah, the way to upload is exactly same as the homework. Okay, now let me share with you where to find this button. Okay, let me know if you see it. You see right here on my purple area, here is midterm, but you won't be able, you won't see it at this moment, but you will be able to see it tomorrow because it's not open for you yet. So midterm and the final. So both are here. Okay. So once you click in it, let me see if I click. It's just like the homework. Okay. The submission process is just like the homework. So you will click on this. It will pop up a PDF file. Last semester, somehow the final for one class, I have problem of this. So if tomorrow I have the same problem, I'm going to put this exam and the course material. So then you won't be able to submit through this anymore. So let's hope tomorrow will not have any problem. It happened last semester. So hopefully tomorrow everything's fine. So you can submit, just like submit your homework. Okay, any other questions? Okay, let me make, let's make this clear. So tomorrow, so this exam will be open book. Open book means you can write down any notes you want, all right? If you have some homework, right, you can consult with your homework, with your notes. You can write down any notes you need. And you need to turn on your camera before the exam. I need to check everyone's identification. When you submit, so make sure you write down your name, your student ID on the exam. And when you submit with your student ID on each page of your work. Let's see, anything else? And it will take 2 hours. You will get 2 hours to finish the exam. If we start late, you know, we'll finish late also. Let's see, anything else? That's it. I will give you 5 minutes more, 5 more minutes. Let's see, if we start at 1, we're supposed to finish at 2. Then I will give you 5 more minutes to submit, for submission. And I think some of you, you know, most of you will finish exam early. Then once you finish, you know, you submit, you're done. Yeah, I will give you 5 more minutes for extra time for submission process. You need to have your camera on before you leave the room, before you leave here, all right? You finish the whole thing means you finish submission, all right? You verify with me. Once you submit, you verify with me if I received it. Sometimes I don't receive because the system sometimes, you know, have some bugs. So make sure once you submit, you know, you let me know. You type in the chat, maybe you said, have you received my submission? And also I can check on my side if I have received it. Then you can turn off. If I haven't received it, you can turn off your camera. You're done for the exam. So when I'm taking a picture of my exam with my phone or camera, I won't be accused of using digital notes. No. No, only for your submission, you can use your phone, right, to take pictures, or your scanner to take pictures, to scan. Okay, I think you guys are prepared for the exam, right? It seems you're doing very well in classwork and also in homework. Any other questions? Okay. Sometimes exam question may be a little bit, you know, harder because for a teacher, you know, we give easier questions, you know, then we give like a medium questions, then we raise the level of difficulty, we give some hard questions as well. So make sure to understand the content of the mathematics. But let me check. I think so. It covers 1 to 5. Okay, let's just review what's going to be covered for the midterm. Remember talking about sets and subsets, right? Elements and a set. We use a notation. An element is in the set is a notation like a E-like, right? Or talk about subsets, we use another notation. So make sure you know, when element in a set, you use one notation. When a subset when a set is a subset of another set, we use another notation. So make sure, and anything, so element has no wiggly parentheses, right? But if we put an element inside of the wiggly parentheses, that makes a set. So make sure you understand those different ideas. So with two sets, we talk about something called a Cartesian product. The Cartesian product is a list of the ordered pairs, where the first member in the ordered pair comes from the first set. The second member in the ordered pair comes from the second set. Then we just permute those elements. Then with sets, we'll also talk about the intersection of sets and the union of sets, the complement of a set, right? Remember those. When we talk about the complement of a set, that refers to we have a universal set. So make sure we understand those ideas. And also with set, we have two kinds of sets. We have a set with a finite elements that we call finite set, but most sets are infinite, like talking about numbers, right? Integer set is an infinite set. And with the infinite set, how do we represent? Inside the wiggly sign, we put dot, 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 right? Put dot, dot, dot to represent their infinite many elements in this set. Then with sets, we're talking about Venn diagram, right? Venn diagram is a picturize the intersection, the union, or the complement of a set. We'll talk about, what is we combine with all those sets, complements, union, intersection, maybe one set subtract another set, so on and so forth. These kind of questions, make sure you do step by step, right? Step by step. Sometimes it's combined with, the complement of a set, then union with another set, then complement of that set. So you do inside and out. You do step by step. Of course, talking about statements, we have a statement true, or a statement is false, or a statement is open statement, open sentence. Then we use the truth table, right? We given us two statements, right? We can talk about one statement, the first statement, and the second statement, or the first statement or the second statement, or maybe negate a statement, or maybe one statement implies the second statement, or the first statement implies the second statement, and the second statement also implies the first statement, the if and only if condition. So for complicated, negation or an and or imply, we always try to use a truth table to figure out. Right? We read the statement, maybe P statement, P, we use one statement, we use P to represent. Second statement, we use Q to represent. Third statement, we use R to represent. Then the permutation of these three will give us 8 different permutations, right? Because 2 by 2 by 2, it should be 8. A true, true, true until false, false, false. So we need to permute the true and false for 3 statements. So we should have A rows to work with. Then, we'll figure out maybe we have a P or Q, or P or R, or maybe Q or R, or maybe Q and R, right? We'll make each column. So make sure do step by step, with logic. It's super important. It's super important to do step by step. And maybe we will also use truth table to prove. Remember, we call it equivalent logic, right? Then, of course, today we talk about those two quantifiers, for all and there is. And then when we negate for all, that becomes there is. When we negate for all, that means we have at least one counterexample. We use this kind of proof all the time in math. If we want to negate there is, that means for all. So those two quantifiers. And of course, today we also talk about we want to negate a composite statements, which means a statement made of 2 or 3 statements, right? It's still a statement itself. When we negate this statement of, made of couple of statements, we have to be careful. And then there's extra credit. If you don't have enough time, forget about extra credit. But if you do, you can try it. Okay, so if you don't have any question with the homework, if you think you can master all the homework, you will master this midterm exam. Nothing is surprising. Okay, any questions? Oh, okay. Ada is asking, can we get the solutions for homework 5? Let me leave you some time for homework 5. So give me a time. Let's vote for a time. I should upload solution for homework 5. Because you need to earn credit before I upload solution. 2:33. 2:33 would be too early. You mean tomorrow? No. Patrick, what do you mean by 2:33? It's 5, but 2:33 is too early. You won't have time to do homework. So I need to leave you a couple hours to you can try your homework, finish your homework, then upload to get credits. So 5 is good for everybody. So if 5 is okay, 9. So 9 p.m. Okay, so 9 is good for everyone. Anybody opposed to 9 p.m.? Yes, we are voting right now. So I think most people agree on 9. So 9 p.m. is good for everyone. All right. So 9 p.m. is good for everyone. So now let me set my alarm. 9 p.m. Oh, hold on a second. 9 p.m. You know what? 9 p.m. Because I have a meeting tonight. I have a meeting at 8 o'clock. Okay, 9. I'll try to remember 9 p.m. If not, my meeting finishes at 9:30 to 10. But I'll set my alarm 8:56 p.m. All right. Okay, I set up my alarm for 9 p.m. Hopefully I have a meeting from 8 to usually 9:30 to 10. If for somehow I didn't post at 9, so you can expect at 10. All right. But I'll try my best. I set up my alarm to post at 9. Okay, great. And tomorrow, let's get online a little early. So if you, just in case you have a last minute question to ask. So I will be on probably around 12:30 tomorrow. So if you have any questions, we can do that. Hopefully everyone can get up a little early so I can check your ID, everything. All right. Any other questions? Okay. Okay. All right. I'll see you tomorrow then.